All right. Ready for an easy day? You will learn nothing new today, which is kind of nice. Okay, and you're going to find that a lot this year. A lot of what we do will be a repeat because we overkilled last year, and you get to reap the rewards of that at times this year. So, yes, always give me y'all's homework, anything that was due. I mean, anything that was signed between this time and the last time.
Do you want to staple together?
No, you don't need to staple together as long as it's got your name on it, or at the very minimum, all yours are all together. I'll be fine. Oh yeah. So y'all have probably a couple assignments in there at least. All right, so here's what we're going to need to do today. You guys are going to need to go back and brush up on your 19 basic functions. All right? I normally give a quiz over that, and I'm not going to do it this year, which really stinks for you because everybody did really well on the quiz. But I'm just having, I would have to give it Tuesday, and then skip a day, and then come back to it. A lot of times I think the quizzes that I've given in the past, I just very well may not give to you. Unless it's something that I could give on an online quiz, just make it up, but graphing on an online quiz just doesn't work real well. So anyway, I was going to hand you this exact thing. I mean, literally it would look exactly like this and say, draw out the line. So you have to be able to do that. So if I were you, I would be preparing. Most of you are fine with this. I'm just going to quickly walk through here and remind you about the things that are important to me if you graph this on your test, because on your test you will need to do it, all right? So if you're graphing a line, just make sure that when you go through the origin, you're not sloppy. And a lot of people start out like this and then just kind of get sloppy like that. Make sure your slope's 1, basically. You're probably not gonna have a lot of these basic functions on your test because we're gonna start shifting and stretching and reflecting them and doing all that. But just make sure that you're hitting all those crosshairs if it was a basic line, okay? So I'm probably not going to mark any points just because it's a line, right? And then on the parabola, y equals x squared, I really just want 3 points, 5 tops. I definitely want the origin. And then if you plug a 1 and square it, you get a 1. If you plug a 2 and square it, you get a 4. And then the same thing, a -1 quantity squared would be 1, -2 quantity squared would be 4, and you really can't go out to 3 because you're out of room, right? So make sure those points are visible, or if they're not, make sure you go through the right points. I don't care if you mark them, as long as you go through them. But if you don't go through them and they're not marked, that's a good way to get dotted or whatever, depending on how far off you are. So anyway, and I realize some of you guys' handwriting is not like super great. That's why the points are great. You can get a point in the right spot as long as you're getting through the points you're okay. All right? Or getting close to the points. Y equals x cubed. Okay, and by the way, we are on, what page is this? 23. So we're on page 23 if you're at home. And so 23 if you're at home, virtual people and blue team for today. Y equals x cubed. I know it's tough to see that, but the x cubed graph, I really just need 3 points from you, and the knowledge about 2 more. This is what I mean. I definitely want that, the origin. And if you plug a 1 in, you get a 1, right? And what happens if you plug a -1? -1, right? Now, what happens if you plug a 2 in there? You get 8. Well, every year I see people do this. This is wrong, by the way. And it looks pretty great. But what are you saying about the x value of 2 right now? You're saying if I plug a 2 in, I get about 2.7 or 3 or something like that. But you don't, you get 8. So on this graph, I can't even get that point 2.8 in here. But I do need to acknowledge that if I were to be able to get it in, if it's somewhere up here, that 8, then you can't be past the line x equals 2, can you? Because you're just not there yet. So same thing over here at -2. -2 would be down here at -8. So just make sure when you do that, that you're kind of leaving out the bottom, not quite at 2. And that's the only thing I'm looking for there. And again, if you didn't do that, you went a little fat, then you're probably going to get dotted on something like that. It's not a huge deal, but anyway. What about absolute value? What do we know about that? That's the V graph, right? So again, make sure you don't just randomly draw me a V, but the slope is 1 this way, and it's -1 that way. And do you remember what absolute value really means? What do we always do with absolute value? Sometimes it's positive, sometimes it's negative. So really, this is something we probably didn't talk about at the end of last year because we were out of time. Due to us skipping, having so many days we lost. But basically what this means, it's a piecewise function. That means that sometimes the graph is going to look like y equals x. And there it is, y equals x, just like number 1. Except not forever, only from 0 to the right. So we say only when x is bigger than or equal to 0. And then sometimes it's going to look like a y equals -x. When is it going to look like that? When the x is smaller than the 0. So that's what the definition of absolute value means. It's a piecewise function. You could write that piecewise function like this. The function, like if I were to write that, you would go, oh, it looks like y equals x along this section of the graph. Looks like y equals -x on that section of the graph. And then once you drew it in there, you go, oh wait, that's just the absolute value function. Well, that's how absolute value is defined. All right? And we talk about that, really, today we start talking about that in the other class, about the and or greater and less than in my Algebra 2 class. So anyway, that's absolute value. Remember square root? Y equals the square root of x. If you forget it, what are some good numbers to plug in there? 1, 4, 0. You can plug 9 in, but you don't have an x value of 9. So again, I look for 3 points on that. If I plug a 0, square root of 0 is 0. If I plug a 1, square root of 1 is 1. And if I plug a 4, square root of 4 is 2. I can't plug in negatives, so all I have are 3 points. That's good enough for me. Greatest integer function. Most people aren't, it's not their favorite function on the planet, but it is Algebra 2 pre-calc topic. What is the greatest integer function to tell you essentially to do with any number you plug in there? Y'all remember? Take a guess. No, you can't plug integers in there and you do get value. You can plug anything in there. What do you do? Like if I were to plug in 3.4, what does the greatest integer function do to 3.4? Rounds it down. It rounds every value down to the next least integer. Okay, so basically what it means, when they say greatest integer, they mean if you had a number line, okay, and I give you a number, they want you to say basically this: what was the greatest integer you came to on your journey from left to right to that number? So if I plug in a 3.4, what's the greatest integer you came to on your way to 3.4? 3. If I plug a 5 in there, what's the greatest integer you came to on your journey to 5? 5, because you got there. If I plug a negative 2.7, careful on this one, what's the greatest integer you got to on your way to negative 2.7? Negative what? Negative 3. You're always rounding down or to the left on the number line. So think about what that means. And by the way, when I'm graphing it, I'm not going to think about it. I got a really quick way to graph, so I don't have to think and I can just move on and don't get bogged down. But here, essentially, this is what you do. Any integer I plug in there, I'm going to get that integer, right? Because I don't have to round it down, it's already there. So if I plug in a 0, it's a 0. A 1, it's a 1. A 2, it's a 2. So I'm going to go ahead and mark points like I'm graphing the line y equals x. And these are closed-in circles. I'm going to mark all of those, which is a great first start. And then I want to think about, I'm just going to think about this with one interval and let you decide about the rest. All right, let's start with 2. You just told me that 2 goes to 2. What would 2.1 give me if I plugged it in there? Also 2. What would 2.2 give me? Also 2. 2.3. 2.4. 2.5. So anything I plug in between 2 and like 2.99 is going to give me 2. But what happens the second I plug in a 3? It jumps to 3, right? So what would be right there? An open circle. So when I do that, I'm going to now extend that thinking and go, well, if that's true for all of these, if I start with 3 and do the same thing, and then 4, then really a shortcut would be to just put all your dots in, and then 1 unit to the right, put a bunch of open circles, and then just connect those two horizontally. And that way you can kind of turn your brain off and just get done with it and move on. Are y'all with me? The way you would see something like that at a math tournament would be like this. Maybe. So what's E? Ballpark me. 2.7, so the greatest integer function is 2. What's pi? 3.14, so the greatest integer function is 3. What's 3.9 repeating? Trick question. 3.9 repeating is actually what? 4. What's the greatest integer function of 4? That bothers people, but it's true. A 0.9 repeating, remember how like a 0.4 repeating was 4 over 9? And a 0.5 repeating is 5 over 9? Well, what's a 0.9 repeating? 9 over 9. It's 1. So a 3.9 repeating would be a 4, and the greatest integer function of 4. So you'd end up with 3 when you add it up. That's the way they ask you about greatest function. There's another name for a greatest integer function. It's called a floor function, because you're rounding down. And another way to write a floor function is like this. Another way to write that is, so whether you saw that or that, it means the exact same thing. And just so you know, there's also something called a ceiling function. What do you think the ceiling function notation is? If that's the floor. Flip it up. Exactly right. That would be the ceiling function. And what do you think this is not equal. What does the ceiling function do? Rounds up. So I didn't even learn that until I was making the key out for a math tournament test. And I'm like, what the heck are these notations? I never learned it in high school, but they do show up, especially if you go to like Vestavia or somewhere, which again, I don't know that we're doing that, given the current state of affairs, but we'll see. All right? And obviously, I would have a hard time making you go and put yourself at risk with a bunch of crazies that aren't documented and whatever. So I just can't even fathom that happening. And I'd have a hard time making you do it. I mean, I'm pretty comfortable because I've got a little immunity at the present time, but I don't know how I could, in good conscience, if you were worried about it, make you do it. What about the 1/3 function? What's another way to write x to the 1/3? Cube root of x to the first. So that's the same thing as that. And then if I'm doing a cube root, what would be good, nice, clean numbers to plug in there that you could do in your head? 0. So cube root of 0 is 0. Mark that. Give me another one. 1. Cube root of 1 is 1. Give me another. 8, which is off the page, but I can kind of squeak it in there. Cube root of 8 is 2. There's 7, there's 8, so that would be up 2. And then what's different about a cube root and a square root as far as your domain? Do what? It can be negative. So I could also plug a negative. Remember, negatives in odd roots don't give me odds. So if I plug the -1 in there, I just get a -1. A negative 8 in there, I get a -2. Now, even though you can't mark those 2 points, why are they good to know? So that I don't go too high with it. And again, if you do this on your test, or on a test or something like that, I'm going to look at it and go, they didn't know, they didn't think about that, you're going to get dotted. So you're going to lose on, it's probably a 2-point question maybe. You're going to lose a half a point. If it's a 4-point question, you might lose a point. But make sure that you recognize that this really does something like that, and like that. And I gotta be honest with you, I'm gonna be at my most pickiest on this test, and then after that, really for calculus, you just need to know this thing's moving that like this. They're not gonna get picky like that again, most likely. At least in the application that you would use this with. What about this one? What is this essentially telling you to do? What's the 3 telling you to do? Cube root it, and then what's the 2 telling you to do? Squared it. So square it. I kind of like doing this, thinking of it like that. That way I can plug the numbers I know in there, and when I'm done, I just square them. But if it's a cube root, I'm allowed to plug in negatives, but when I square it, what's it become? Positive. So this negative part down here is going to get flipped up, but when I square it, typically what happens when you square values? They get bigger, a little bit bigger. Not always, like fractions that are between 0 and 1 get smaller, but everything bigger than 1 is going to get bigger when you square it. If you think about that, that'll make sense. Like if you square a half, you get a fourth. But if you square 2, you get a 4. So I can still plug in a 0 and get a 0. I can plug in a 1. Cube root of 1 is 1. 1 squared is 1. And I can also plug in a negative 1. Cube root of negative 1 is negative 1, but when I square it, I get a 1. But what happens when I plug an 8 in? I get 4, right? Because the cube root of 8 is 2. 2 squared is 4. So again, I'm going to visualize 8, but I'm going to now not be at 2. I'm going to be at 4. So for you, sketching it, I just need to see that you know it's a little higher. And if it's going to hit 4 there, as long as you exit your graph somewhere between the 3 and the 4, I'll know that you've kind of visualized that. So I'm just going to come up here and make sure that I exit somewhere between there and there, the graph. On my way to that. Not too bad? Okay, last of these. Logs. Okay, that's one of those things that people either loved or hated, learned the rules, struggled with the rules, memorized them, whatever. Nice thing about logarithms is when you get to calculus is we do very little of all the rules that we learned, just a couple things you need to know. And most people, even my reeker of calculus students, learn those couple things and they're fine. You guys won't have any issues with it. We won't even deal with log base 2. We'll only deal with natural logs and base E exponents. What did I skip? That. Okay. Coming back to here, we'll come back to logs in a second. Y equals 1 over x. What's that essentially mean? If I plug in an x, what's the y value going to be? The reciprocal. Good. So if I plug in an x, I get a reciprocal. So am I allowed to plug in a 0? So if x is 0, I get undefined. That's a vertical asymptote. It could possibly be a hole if there was a 0 on the bottom, but we'll talk about that later. All right, what happens if I plug a 1 in there? What happens if I plug a 2 in there? Half, 3, third, 4, fourth, 5, 5th, 6th, 6th. Am I ever going to hit this line? No, because I go 1/7, 1/8, 1/9. So what do you think's happening if the graph is getting closer and closer to that? What does that represent then? It'll get closer and closer but never touch it. It's a horizontal asymptote. And we're going to talk a lot more about asymptotes later. All right, what happens if I plug in a 1/2? I get 2 and a 1/3, 3, 1/4, 4. So you can see not only is this following the asymptote that way, but it's following the asymptote that way. And so the points I want to see basically are just that one, and then the knowledge that you know there's a vertical asymptote, a VA, and a horizontal asymptote, an HA. And then what happens on the right side, on the left side? What happens? Basically does that. But what point do you think I want you to mark? -1, -1. And then as long as you mark that and go, all right, I know there are asymptotes this way also. And if you think about it, if I plug in a -2, I get a -1/2, a -3, I get a -4, a -4, I get a -4. As long as you know those 2 points right there and know that it follows the asymptotes, you're good. What about this one? What do you think the square does to the left side? It makes it positive. So I can still plug negatives in, but the results are positive. So this ends up looking like the volcano. What do you think the squared also does? Not only does it make it positive, but what do squared numbers normally become? Bigger. So what that means is, for values like a half, when I plugged in a half here, I got up 2. If I plug in a half here and square it, I'm going to be up 4. So it rises faster. And because it rises faster, you're still going to go through these 2 points, right? Plug in a 1, get a 1. Plug in a -1, get a 1. And you're still going to have a horizontal and vertical asymptote for the same reasons, and you can see that when I plug and chug numbers in. But the difference here is it gets down more quickly, and it rises more quickly. And because it does that, it's a little more open at the top, right here. I know this is not the greatest graph, but you see how the openness here is a little bit more than right here? Right here, that line is already really close. But here, because at 1/2 I was already at 4, it's a little open at the top. So I'm not going to quibble about that. If you were to graph something like this over here and it almost looks exactly the same, it's not really open a little bit at the top, it's just not that important. But the reason we call that the volcano graph, it is a little bit more open. It's not squeezed tight, so it's a little bit bigger opening there. But anyway, what's that next graph? And by the way, it may not look like this. It may look something like that. What's it called? It's a semicircle. If I were to square both sides, check it out. If I square both sides, and then I move the x over, most people look at that and go, oh, that's a circle. And they draw a whole circle. The only problem is, even though that's a circle, the original problem doesn't let me get all of the values. Think about it. No matter what I plug in here and square it, and then subtract it from 16, if I were to end up with a negative value, what's the square root of a negative? Imagine it doesn't show up. So there's no way for me to get a negative y value. There's only a way for me to get positive y values. And if I can only get positive y values, where do you think the semicircle shows up? On the top part. So you can think about it as a circle with a radius of 4. You can think about it like this to start, but because y equals a positive radical, the negative y's don't show up on this. So don't make the mistake of going, well, why can't I graph that? It's kind of like this. This is a more simplistic way of thinking about it. What if I said to graph the line x equals -2? Wouldn't you come in here and graph a line where it crosses x at -2 right there? But look, if I go and square both sides, and I start doing algebra to it and then square root it again, I get x equals plus or minus 2. So does that mean just because I did a little algebra that I changed this into something completely different? Now it has two lines. No, you always got to go back and look at the original domain, the original problem, and this says y is positive. So I have to stick with just that part of the semicircle. And hopefully you'll just recognize that and go, oh, the radius is 4, and that's a semicircle, so I'm just going to go out 4 and move it up because it's plus. Now, if it was minus right here, then what would you do? Yeah, you do just the bottom part and not the top part, but this one's plus. All right, what about exponential functions? And by the way, you might see one with a 2, with a 3, and it's also possible that you see one with an e. I'll do the e in a second if you want to see that. But with this one, what would you do to graph it? Plug in some points. Now, I only need to see 2 points on this graph. All right, and then the knowledge of one other thing to help you. So if you only need to see 2 points, what x values would you probably plug in? 0 and 1 would be 2 great numbers to pick. If I plug in a 0, that's great because anything to the 0 except 0. Any number to the 0 is what? 1. So if I plug a 0 in there, x equals 0, y is 1. And then if I plug a 1 in there, y is 2. Now, because the base is 2, I could also plug a 2 in and get 4, so why not? But if that base is any bigger, I'm not going to have room to graph that third point anyway. So 2 points, and then what do you know about exponential functions in general? They always start out flat and get bigger, or they start out big and get flat. So what kind of asymptote do they have? Horizontals. And the horizontal asymptote, as we'll talk about in a second, is always that shift. Well, there's no shift on this graph. Right? I don't have like a +5 out to the side that shifted it up 5, which we'll talk about in a second. So if there's no shift, then the horizontal's right here. Well, if I have these 2 or 3 points and a horizontal, what's the graph doing? Yeah, it's just connecting the points and then going, well, this one, if it looks like it's going down, it must follow it out that way, must head up. And the only difference for you that might give you a little trouble is what would you do if there was an e there? What if it was e to the x? What does e about mean? You already said it once. 2.7? Okay, well let's do the same thing. What numbers would you pick to graph this? 0, plug in a 0, what do you get? 1. What other number would you plug in? 1. If I plug a 1 in there, what's e to the 1? E, about 2.7. So if I plug in x equals 1, just go up about 2.7 and mark your point. And again, all I need is 2 points and the knowledge that there's a horizontal, connect the points and follow the graph out and let the graph go up. That's all I need from you. And really that's all you're going to need moving forward. Now if there's a number in front of the e like a 4, we'll talk about that in a second. If there was a negative, there might be a reflection somewhere. We'll talk about that in a second. So far so good? All right, and what about logarithms? Now what is the relationship between a logarithm, and an exponential graph? Do y'all remember? Logarithms and exponential graphs are what of each other? You're thinking right, but it's not the right word. They're not, opposite means plus minus. They're not reciprocals. Rhymes with pinverse. Inverse, yeah, they're inverses of each other. And what do inverses do? They switch what? Y'all remember? Trying to think if that's something we missed. I don't think we missed it, but I know we missed talking about it for the second time at the end. An inverse, all you do for an inverse function is you switch the x and the y. If the function is an actual function, if it's a bunch of points, you switch the x and the y coordinates. So if I've been plugging in a 0 and a 1 and getting answers, and I'm using those points, and I have a horizontal on an exponential function, what I'm going to do is look for the numbers that I plug in to get 0 and 1 for y's, and it's going to have a vertical asymptote. So think for a second. What do you remember about logs? What numbers would be really nice to plug in for this logarithm for x? Do you remember? 1, because anytime I log a 1, I get 0. Now, didn't I have a point on my exponential function that was 0, 1? Now I have the point, plug in a 1 and get a 0. Inverses. So I'm going to mark 1, 0. Now, what other numbers would be easy to simplify if I plugged in here? 2. Remember the rule? If I plug a 2 in and the bases match, you take the exponents. 1 over 1 is 1. So if I ever plug the same number as the base, I always get 1. So what point did that give me? 2, 1. And what point was I using over here on the exponential one? Plug in a 1, get a 2. Now I'm plugging in a 2, get a 1. I'm switching the points. What else could I plug in here? Do you remember? 4. 4 would be like plugging in a 2 squared. If the bases match, I put 2 over 1 and I get a 2. So if I did plug in a 4, I would get a 2. Now, if an exponential has a horizontal asymptote, what does a logarithm have? A vertical. So all I need from you on a logarithm are 2 points. I did 4 because I could, but most of the time you can't. You don't have room for it on the graph. And at this time I'm going to have a VA. And if I'm connecting these 2 points, what choices do I have, right? The only choice I have going to the left would be to follow the asymptote down. And the only choice I really have to the right is just to kind of move out there. So don't make these hard, just give me a couple points. Let me give you another example. What would I do if this was log base e, which by the way would never be written like that. How would it be written? Instead of log e of x, what would I write? Ln of x. But even though I'm going to write ln of x, you think about it as log e. So what quick numbers can I plug in there? I can log a 1 and get 0. And what else? I can log an e and get 1 because they match. And if they match, I take the exponents. So if I plug a 1, I get 0. And if I plug in e, I get 1. And what did you say e was again? About 2.7? So you go out about 2.7 and you go up 1. And all I need is 2 points and what? The knowledge of a vertical asymptote. And then you connect the dots, and what choices do I have? If I have to follow the vertical, and it looks like I'm heading this way, then I must be diving down, and this just must be moving out. And that's all I need from you. Something like that. And if you mark the points, even if you're like, when you're writing, you're going to be fine. If you didn't catch that, if you're writing, you'll be good. All right? Trig functions. I'm going to be very kind of lenient on the trig functions for a couple reasons. One, we didn't get what I like to give you last spring. Okay? So on these, I'm going to be a little loose, a little bit more free this year than I have been in the past. We're going to go back through trig again completely. And then after that, I won't be like this. But just because we're doing a review and we kind of watered them down last year and you didn't get a full-fledged, I mean, you were able to use your notes for goodness sake. So I'm not going to make you go back right now and relearn all of this until I'm going to hold you accountable later. So I probably am going to avoid a lot of these on a test, to be totally honest with you. But just so you remember, do you remember sine curves? If you remember the unit circle, what's the sine of 0 on the unit circle? I'll kind of draw one right here. At 0 degrees or 0 radians, what is the sine is the what value? The x or the y? Do you remember that? The coordinate here is 0, 1. I'm sorry. The coordinate here is 1, 0. The sine is the y coordinate, cosine is the x. Okay? So if I want to know the sine of 0, I think that would be me plugging a what? Talk to me. If I plug in 0 degrees, what's the sine at 0 degrees? At 0 degrees, the sine is the y value. So what do you get? 0. And if this is pi, what would the one in the middle be? Pi over 2, and pi over 2 is 90. So think 90 degrees. If I were to plug in 90 degrees, which is the same as pi over 2, which is right here, sine of pi over 2. What's the sine at pi over 2? 1. So at pi over 2, I'm up 1. What's the sine at pi? That's like 180 degrees. Is this coming back to you? So at pi, which is 180 degrees out here, right? What is the y value at 180 degrees? 0 again. At 270 degrees, or 3 pi over 2, what's the y value? Negative 1. And at 2 pi, which is all the way around, what's the y value? 0. All I need is 4 points, and then from that, I mean, what's the sine curve doing? Just wagging along. So just repeat that period again, and you have your sine curve. Now, I just kind of memorize it. I mean, I have it in my head already burned into my brain. So if you do, great. But definitely crosses at the origin, goes up first and down first on a basic sine curve. What does cosine do to start out? Does it start at the origin? It starts up. Why is that? What's the cosine at 0 degrees? It's the x-coordinate, 1. So at 0 degrees on a cosine, you're up at 1. But what happens at pi over 2? 0, so I'm back down here. What happens at pi? Negative 1. And look, at that point, you're like, oh, it's going down and then up. So it's just kind of wagging along. rolling along like this. And try to avoid the V. Let me get a little curve in there. But I had a dude named Jimmy Vaughn or Charlie Vaughn, I forget, they were the Vaughn brothers. They both had truly, I think they had dysgraphia or something like that, like the worst writing I've ever seen in my life. And I was like, dude, I don't even know what you're doing. Like, I think I told you this last year, like, this was a 6, this was a 4, this was a 9. And I'm like, dude. But fortunately, they were brilliant kids. I think one went to Stanford, one went to Duke. Really bright guys. But for them, I was like, okay, I'm having trouble with your graphs. So can you put the points where they need to be? And they're like, yeah, we know where the points are. So they were able to get the points on there. All right, so I would get this from them. Maybe the points are kind of like, probably like that or something, scribbled in there. And then the graphs would be like, ugh, They would look absolutely horrendous. But as long as the points were there, I was good because I could see what they were doing. Do that. But if you don't want to do the points, that's fine too. But I'm going to be looking to see if your graph was going through them. So if you don't have any points, and that's fine. And you're like, but I know it goes through this one, and then that one, and then this one, and then that one. Just make sure you're really careful. But putting the points in there is helpful to me. And it'll be helpful to you when I'm grading. Tangent. What can you not take the tangent of? And think about that. Tangent is y over x. If you remember the definition. The tangent of an angle is y over x. So when do you get in trouble with tangent? When x is 0. When is x is 0? Boom. 90 degrees. So at 90, and 90 is a half of a pi, half of 180. Or also where? At 270 or negative 90? At negative 90, or at 270. But once you get the pi in there, remember how on the period on a tangent was pi over b, not 2 pi over b? You're like, yeah, I know it was a while. Again, we raced through that stuff. But once you get the 90 in there, just put them every 180 degrees or every pi apart. So pi is 2 ticks. So every 2 ticks, you're going to have a VA. And then what do we remember about tangent? It's all what? It's all right to be tan, up to the right. Did I not give you this lame example? And there's 2 lame ones that our kids have come up with over the years. And you know how when you go to summer camp, when you get there late, what do you have to do? You walk in the room, you're the last guy in there, and you get the only cot left. Cotangent goes up to the left, or in the words of, I won't even say his name. I actually have his sister in one of my classes this year, so when I tell him the story, she's going to go, she's going to know. But this kid goes, well, yeah, and he gave me the summer camp example. And then this guy in the class goes, that's stupid. Why don't we just say it's all left to be caught? I'm like, what does that even mean? And it was so stupid, that's what everybody remembered for the rest of the year. So they'd be in like, it's all right to begin. It's all cut to be left or something, I don't remember. But anyway, if tangent goes up to the right, then just mark in the middle of these lines and up to the right, down to the left. That's all I need you to know on these. I don't need you to apply the period and all that stuff. And then if I just did another one, you would see it do something like that. If I put that one here, it would do something like that. So it would look something like that. But that's tangent. Cotangent's a slight bit different, because how is cotangent defined? That looked a little creepy, the 666 thing up there. Cotangent's x over y. So where do I get in trouble here? When the y is 0? When is y 0? At 0 and 180. So I go to here and I go, all right, at 0, there's a VA. At pi or 180, VA, and then just make it every couple tick marks, every pi or every 180. And then if tan goes up to the right, cotangent goes up to the left. So just make the cotangent, put a point in the middle like before, dang it. Put a point in the middle like before and go up to the left, down to the right, up to the left, down to the right. And I think I normally make you guys graph 2 periods, so you don't have to fill up the whole thing if you don't want. long as you do a couple so I know that you understand the periodicity of it, how it repeats itself, you'll be fine. And then what is secant? Similar, not in looks, but in the way you build it. What is it similar to? Or what does it kind of go with? The cosine? So right here, I'm going to sketch a cosine graph in here. You don't have to if you really got it, but if you've forgotten a little bit, put the cosine in here, because this is the same thing as 1 over cosine. And then let me ask you a question. Where would cosine be 0? Because where cosine is 0, that's where I get in trouble here. I'd have 1 over 0. Where would cosine be equal to 0? At 90? 3 pi over 2 or 270? Look, that means you're going to have a vertical asymptote at 90. Vertical asymptote at 3 pi over 2 or 270. Also at negative 90. Now there's another way to remember that. I can just put a vertical asymptote everywhere cosine hit the what? That line running through the middle, which we call the D value. That's my vertical shift, if you remember that. So everywhere it hits there, that middle line, put a VA, and then what do I do to graph the actual secant curve? Do you remember? It's like a reciprocal, so I kind of just take this part and flip it up. This little U, flip it down. This little bump up, flip it up. This little bump down, flip it down. Flip it up. And you're going to do the exact same thing with cosecant, except you build cosecant off the what? Sine curve. So here's the sine curve in here. And then where do I put the VAs? Wherever that line through the middle hits them, which would be here, 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 here. Now I have a lot of people that don't like putting the vertical asymptotes. They get a little lazy. Why is that a bad idea? Let me show you. Check this out. This is what I normally see when people don't put vertical asymptotes. They go, oh, well, I know it's just at the bottom of that bump, I just bend it down. And they do that, and what did I end up doing? I crossed where the verticals would have been. See, look, if I put the verticals in there, I'll go, oh man, look, I crossed it there, and I crossed it there. And granted, that's not the only thing I'm looking for on this graph. If that's all you did wrong, you'll probably get dotted. But don't get dotted and lose a point or whatever that's worth. So put the VAs in there, or just remember where the VAs would be. And then just keep it in between the lines there. Y'all with me? Again, I normally make this like a 38-point quiz, 19 basic functions, and I think my worst grade is like a 36 out of 38. But it's tough for me if I gave that quiz, and I normally give it tomorrow, you guys aren't here. So they would be getting a nice 38 and you would not, so anyway, and then I don't see you again until Friday. And is our test Friday or? No, our test in here is Monday, Tuesday. For you guys, it'll be Tuesday. So anyway, it's just not like, it's not a conducive situation to do all this. Have we talked about test days in here? We have not. I'm not going to give the test online, and I'm not going to give it to you guys. No, you'll see me, I'm sorry. You'll see me Monday. You're not completely. You'll see me Monday, and but I'm not going to give it to you on a Monday, and then online to Thursday where they can maybe sneak their notes out or whatever. I do think I have a plan to the virtual guys to maybe do a test at home, and I might have you adjust your computer screen and get you in a Google Meet so your Meet is watching you take the test. I mean, not so closely so somebody else in the Meet can watch you take the test, but can see you without your notes, without your stuff, just working away. So I think I may have a plan for that, but to keep there from being an unfair advantage, I'm going to test you guys, and it'll probably be you guys first. But I'll test you guys like on a Monday, and I'll have the blue group do the next assignment in the next chapter, and I'll have them watch a video at home. And then on Tuesday, I'll have them come in to take the test, and you guys will watch a video at home. And that way I don't lose a day, because if I just give you a free day when you're not testing, then they always get an extra day to review. And at the end of the year, we've lost 20 days. Which will be kind of like last year. You just don't get the same education. I don't want that for you guys. I mean, secretly, you're like, I don't have a problem with that. But you will. It starts adding up, and I don't want you guys to be in a deficit. My youngest two kids, you remember Caroline and my oldest son John Michael, no, you never knew him because he's a junior and you guys are juniors, so he was never here when you were here. But they came from a private school. It was great with English and history and humanities and all that kind of junk, but was abysmal in math. And I didn't know it until my oldest child became a junior, senior, and she came back and was asking me questions, and I'm like, oh dear Lord. She had a high A, and she couldn't do the basic things. And I yanked my kids out and sent them here. And even though they didn't know anybody, they thrived here. But my son made a 38 on, I think it was my first Algebra 2 test. My daughter made a 67, and my son made a 34 in his ACT. And it's an actuarial science, but that's just how bad it was. And I don't want you guys to suffer like that, so I'm not gonna let that happen.